This is the last topic for Physics 1, first quarter, vector resolution or adding vectors by the analytical method or the use of components. You have been introduced with trigonometry last time that we can determine the components using the trigonometric functions sine, cosine, and tangent. So you have noticed here we have the x and the y axis, wherein the y could be the north and the x is the east. So we have vector A here, and there's an angle of 30 degrees. So there we have the points A, B, and C, and this is known as vector V. And vector V has components. So it has these components y, vy, and also vx. But take note, you can transfer the vy here on the other side to form the right triangle. So that you can use the trigonometric function sine, cosine, and tangent. So below here, as you have noticed, if you have vx, this is adjacent to this angle theta. So we can use cosine theta is Vx over V. So if we transform it into Vx, so Vx is equal to V times cosine theta. And also we have Vy. Instead of having it along the y-axis, you can transfer it to the other side. And this is the opposite to theta. So we can use the trigonometric function sine theta is equal to Vy over V, wherein V or the vector itself is the hypotenuse. And solving for Vy, is Vy is equal to V sine theta. So take note of this. Is your angle, if your angle is based on the x-axis, your y component is always having the sine function, and your x component is always having the cosine function. So as you have noticed here in the other figure, we have theta here, and this opposite to theta is opposite side, and we have the adjacent side, and we have the hypotenuse. And if you increase the triangle, like you double the lengths of the triangle, so you will determine still the same ratio. So here, this is the general form of SOHCAHTOA. Sine theta is opposite over adjacent or opposite over hypotenuse, sorry. Cosine theta is adjacent over hypotenuse. And we have tangent theta is opposite over adjacent. So that's why SOHCAHTOA. Okay. So if we proceed, we have here's an example. So if we have the vector v, if we have the vector v is 500 meters, okay, this one, and the angle is 30 degrees, and if we are going to have the components vx and vy, so it can be shown that your vy here, which is here to be drawn here, is opposite to 30 degrees, so your vy is p sine theta. And since you know v given is 500 meters, times sine theta, which is 30 degrees, you'll end up with 250 meters. Yeah, this one, 500 times zero point 0.5 because the value of sine 30 is zero point 0.5. And if we have also the Vx here on this side, yeah, this side is adjacent to 30 degrees, so you use V cosine theta, and that is equal to 43 meters. So that's why you have the Vx 43 meters and Vy to 50 meters. And to get the V, of course, you can use the Pythagorean theorem because this is the hypotenuse, the longest side. So it is the square root is equal to the square root of the Vx squared plus Vy squared, and that gives you 500 meters. So there are two ways to specify a vector in a given coordinate system. So we can give its components, Vx and Vy, and of course, you can determine the Vx and Vy. So we'll know this is the x and this is the y. So we can determine whether what quadrant they belong. So we all know that x here is positive and y here is positive, and here x is negative and y is positive in quadrant 2. In quadrant 3, negative for both x and y, and in quadrant 4, positive x and the negative y. So you will notice that if you have the signs of the ordered pairs x and y, you can plot it here, and if your angle is based on the x-axis, so like if you have a vector here, your angle is based on the x-axis, so you will have the sine and cosine function, and also with respect to this. And we all know that if you have a certain coordinate system, the angle going counterclockwise is positive, and the angle going clockwise is negative. So if you say negative 90 degrees, it's going clockwise. Positive 90 degrees is going counterclockwise. And we can give also the magnitude of the vector v, and the angle theta that makes it the positive x-axis so that you can determine the vector. So we can also use this Pythagorean theorem in which we can determine the vector v by the square root of the vx squared plus vy squared or the components. And to get the angle theta, tangent you use tangent theta trigonometric function that's equal to vy of vx. And to get theta, you get the inverse tangent or arctan function in the calculator. So we have the Vy over the Vx. Okay, so this is how to get the components of the vectors. Okay, and let's proceed. Okay, so in this case, you use the trigonometric function. So that you can determine the x and the y components with the Pythagorean theorem to give the vector. So it's a combination of all of those. So if we proceed with a problem, so like this is taken from John Colley, three short trips. An airplane trip involves three legs with two stopovers, as shown in this figure. Then the first leg is due east for 620 kilometers, and the second leg is southeast. Uh, Okay, let me have this. Okay. First, this is an example on how to add vectors here. We have V1. Take note, we have V1 here as drawn. So we have V1. And we have V2 also by tail to tip model. So if you add them, so just connect from the tail of the first vector to the tip of the last vector. So that's why it is the VR or the V1 plus V2. And if we deal with components, so for V1, this is the V1x component, and for V2, this is the V2x component. So if you add them, that corresponds to the resultant x component of the VRX, this one. And for the y component of the two vectors, this is the V1y and this is the V2y. If you add them, this corresponds to the V resultant y. So it corresponds also to our tail to tip model in the component method. So now let's proceed to the problem that I mentioned a while ago. So an airplane trip involves three legs with two stopovers. And the first leg is due east for 620 meters. So here, D1. And the second leg is southeast, 45 degrees. So this is how to have the 45 degrees here below the positive x-axis because it's positive 45-degree angle. So meaning it's a positive angle for 440 kilometers. So of course, you can do the tip-to-tail method. So D1, and then this one, D2. And then the third leg is 53 degrees south of west. So south of west, you measure here from the west, the horizontal, the negative x-axis, you measure 53 degrees. So that's south of west, and this 50 kilometer. And by tip-to-tail method, so the resultant is somewhere here. So by just drawing the tail to tip method graphical way of resolving vectors, you will know that the angle is below the positive x-axis. Okay, so how to solve it using the component method. So if you use the component method, we can have this. First, draw a diagram. So of course, you can draw a diagram, represent the vectors d1, d2, and d3 for the three legs, and the dr is the displacement vector. So this is how this is drawn. So the illustration is showing here the tip to tail method, the d1, d2, d3. And then choose axis. Axes are shown in figure 3-16a. So we have the x and the y. They are the x and the y. And then resolve components. So it is imperative to draw a good diagram. The components are drawn in this figure, okay, here. Because D1 is along x-axis, so it's drawn. There's no y component, so only D1 has x component. And D2 is having both the x component, the D2x, and we have the D2y here. And of course, this is an angle of 45 degrees. And D3, of course, you can also have the x component here and the y component. So it will just show that both tail to tip will give you the same answer because if you connect it and you will get the same answer. Okay, so how to have the components now? So you can have D1x um, is equal to d1 cosine 0 degrees because it is 0 degrees here. So the d1 is 620 kilometers. So times 1, cosine 0 is 1, so 620 kilometers. And d1y, d1 sine 0 because it's 0 degrees, so it's 0 kilometers. So it's obvious because there's no y. And for d2x, d2x is here. It's 45 degrees uh, angle. So it is cosine 45, d2 cosine 45 because the angle is based on the x-axis. Yeah, if you have noticed here, 45 degrees below. So in this case, it's 311 kilometer for D2X positive. Okay, so just get the value of this in your calculator and be sure it's in degree mode. And for D2Y, negative D2 sine 45 degrees. Why negative D2? Take note, this is um, going down. So in this case, the D2Y is negative. This one is going down. So you affix there the negative sign. Please don't forget that one. If it's going down, that's negative. And then 440, because that's the value of your vector, which is the hypotenuse, the D2 here, and then times the sine 45, which is 0.707, it will give negative 311 kilometers. Similarly for D3. For D3 this time, this is the case. So D3, if it will be resolved into its components, so you can have there the uh, d3x in this direction, which is negative, and d3y also, which is negative. Similarly, you can draw the vectors this way in separate lines. Do not by tip to tail. This one is just showing you how to draw the tip to tail model with the components. So if this is d1, so you can draw d1 that way. Yeah, so yeah, if we are going to use the Cartesian coordinate and they will be separated from each other. So D2 is 45 degrees below uh, positive x-axis. So you can have D2 also here. And this is 45 degrees. So this is another way of showing those vectors. So in this case, you can have the components also. The y, this is the D2y, because this is the D2y here. And yeah, and then the D2X here. So you can also do that. And then the D3 is 53 degrees because D3 here is 53 degrees south of west. So D3 will be here. Okay, D3 will be here. And of course, you will have 53 degrees here. And if this is D3, this is the Y component down, and this is the X component to the west. So that's why both are negative. So that's how also to show, aside from having this tip to tail method coincident, or um, we have shown the tip to tail together with the component method, you can also separate those vectors, and you can have that. Okay, so after solving all of that, so we can have a table. We have x component and we have y component, and you add them. So you add also the y component. So you have now the drx and the dry. So after having the drx and dry, so this one way of representing vector. So you'll know that it is in quadrant 4 because we have 600 negative 750. So it's in quadrant 4, so we expect a negative angle because in quadrant 4, we all know that if your angle is counterclockwise, it's positive, but if it's clockwise, it's negative. So since it's quadrant 4, it will be here. So it will be negative, the negative angle. And we have a negative y and a positive x. Okay, so you have there drx 600 kilometer and negative 750 kilometer. And to get the resultant, if what is the plane's total displacement, because this is the goal, to resolve it into by using the analytical method, is you are going to use the Pythagorean theorem. So square of drx squared and dry squared, because if you plot it in the Cartesian coordinate, it is somewhere here. Okay, so this is your resultant displacement, dr. Okay, because this is having an angle of negative 51 degrees by having the arctangent. So here dry over drx, that is tangent theta, so you have a value. And then to get that one, so you have tangent inverse or arctangent. So you have a negative 51 degrees, meaning it is below it is here, negative 51 degrees. So if negative 51 degrees, so you can have the y component downward here and the x component here. If that's negative 51, on the other side, it's also complementary. So it will be 49 degrees. So you can also use this side to solve for the components or the negative 51 degrees to solve for the components. Okay, so that's how to get the resultant 960 kilometers and the angle negative 51 degrees. There's a tangent theta value, this one, and you will just get the arc tangent or the arc tangent or the tangent inverse in the calculator. Okay, so that's for resolving vectors into components and finding the total vector or resultant vector. Okay. So now let's proceed to relative velocity, the application. For the application, relative motion or relative velocity depends on the reference point. So for example, if you have two cars moving towards each other at 60 kilometers per hour, so you will expect that with the reference of, because you are in the car, and since they are towards each other, so you will have a velocity of 160 kilometer per hour with respect to the other because they are moving towards each other. But if they are parallel and the other car is 90 kilometer per hour, the other is 70 kilometer per hour. So if you are in the 90 kilometer per hour, so you will expect with respect to the second car, which is 75 kilometer per hour, you just subtract. And that's the velocity with respect to the other car that is moving. So similarly, if we are having two objects not in the same line, moving not in the same line, we are going to use vector addition or resolution of vectors. That's why this is an application. So each velocity is labeled by two subscripts. The first refer to the object and the second to the reference frame. So what's good in here is because if we have this notation wherein the first subscript is the object, so we will take note, like for example, there is a boat going to the other side of the river bank, for example. So if we want to determine the velocity of the boat with respect to the shore, and we just know the velocity of the boat with respect to the water, this one. So the velocity of the boat with respect to water. So here, boat is the first um, subscript, which is for the object, and W water is for the reference frame. You can add it to the velocity of the water with respect to the shore. So meaning it is the river current. So there is a river current, and because of that, ma-affected ang velocity of the boat if you are on the shore and you are going to judge what's the velocity of the boat with respect to the shore. So by this notation, we can use this velocity of the boat plus velocity of the uh, water with respect to the shore. Take note, the water here is in the inner part, and in the outer, it corresponds to B and the S, which is what we are going to determine, the velocity of the boat with respect to the shore. So that's why this notation is important, because the inner is to be canceled and the outer is the resulting one. And since it's adding, you can just use the tip to tail method. So like velocity of the boat with respect to the water, velocity of the boat with respect to the shore, and you connect from the tail of the first vector to the tip of the last vector. So this is now the resultant, which is the velocity of the boat with respect to the shore. And it's also applicable to three vectors, like for example, velocity of the fisherman with respect to the shore. If there's a fisherman in the boat, so we have Fs with respect to the shore. So we start with F because this is the first subscript. So we need to know the velocity of the fisherman with respect to the boat if the fisherman is there inside the boat and it's moving and the fisherman is moving. And next is we have to cancel the B here. So therefore we need to know the velocity of the boat with respect to the water. So they are inner. And aside from that, since we have W now, and we have to know the velocity of the river current or velocity of the water with respect to the shore. So cancel also the W here, which is inner, and to give F and S. So it's just like adding all vectors because they are constant velocities. Okay, so that's the same thing with vector resolution. Okay, so that's for uh, application, relative velocity or relative motion as your last module there. And the next is a problem taken from John Coley. So like, for example, heading upstream, a boat speed in still water is VBW is equal to 1.85 meter per second. So in this case, we have here the velocity of the boat with respect to the water, this one. Okay, so a boat speed in still water is 1.85 meter per second. If the boat is to travel north directly, so your goal is the boat must travel directly north, but there is a westward current. So therefore, if there is a westward current, you have to uh, position your boat such that you have to orient your boat such that the westward will be compensated by the eastward direction. So that's why it is this way, in this manner, the boat. So there is an east component that will somehow compensate with the westward component of the river current. So we have the velocity of the water with respect to the shore is 1.20 meter per second. So this one. And then you are asked what upstream angle must the boat head so that it will compensate the westward. So it's asking for the theta here, the upstream. So we have here the velocity of the boat with respect to the shore is to be the resultant. And you're asked about theta. So obviously, since it's a right triangle, you just have the trigonometric function sine theta because you all know the VWS, you know this, and you know the VBW is the sine theta, it's opposite over hypotenuse. You all know that the hypotenuse because it's the longest side. Okay, so it will give you 0.6486. And in your calculator, you will just press inverse sine or arc sine. Yeah, so you can, and then this one, and then you can get the angle as 40.4 degrees. Okay, so that's an application. And next is another problem there in John Colley. Here, it's still with relative velocity. It's the same boat with a velocity of 1.85 meter per second. This one, and then now heads across the river whose current is 1.20 meter per second. So it's directly the boat is heading directly across there, the river, and then there is a still current 1.20 meter per second. So this one, water with respect to the shore, and you're asked what is the velocity of the boat relative to the shore. So if you want to know VBS, so you assemble VBS. So your first vector must have the first subscript as B, and then the last vector must have a subscript of S. So that's why we have VBW, both with respect to water, and water with respect to shore. So the inner subscript will be canceled out. So to solve for this, you use the Pythagorean theorem. So this is the resultant and square root of the VBW squared plus VBWS squared. So that's why you get 2.21 meter per second. And to solve for the angle, because it is asked here, if the river is 110 meters, how long will it take to cross the and how far downstream will the boat be then? So we can obtain the angle because we can use this. Yeah, if we want to know the angle also. So you can have the tangent theta, WS, opposite over adjacent, BBW. So there, 0.6486, and arc tangent, it will give you 33 degrees. So take note that this is the different angle to the previous example because now the boat is heading directly across the river. And the travel time for the boat is determined by the time it takes to cross the 110-meter wide river. So, excuse me, we can use the velocity component and direction of the D. Okay, the velocity component, which is the V. In this case, we have there solving for time, D over T, in the direction of D. We have there 110 meters divided by um, 1.85 meter per second because the this one is 1.85 meter per second, the VBW. So there it's 59.5 second to cross that one using the VBW. But the boat will be carried downstream this time. So a distance, because you're asked how far downstream. So the distance is you will be using VW as here times time because it will be carried by the current. So there, 1.20 meter per second times 59.5 seconds. So you'll get 71 meters. Okay. So take note, this is relative motion or with having with constant velocity and not with accelerated motion. So this is the application and the last part of the first quarter. So please prepare for a checkup quiz on this next meeting. Okay. Thank you for listening and you just study for the last checkup quiz on Monday.